Hello friends, in this video we're going to talk about the effects of quantization on FIR filter coefficients. These are the topics we're going to talk about today. I have a couple of design examples where we're going to show what the effects of coefficient quantization is in FIR filters. We're going to talk about what you can do about it and what design trade-offs you have to work with. We're going to do a brief overview of the quantization noise formula, and we're going to use that to develop a rule of thumb for coefficient bits, and finally wrap up. We're going to go through an example using a filter that has a sampling frequency of 100 kilohertz. It's a low-pass filter, has a pass band frequency of 10 kilohertz, a stop band frequency of 11 kilohertz, 1 dB of passband ripple, and 80 dB of attenuation. And if we optimize this on ScopeFIR, we come out with 259 taps to implement this filter. That's using a full precision implementation internally in ScopeFIR. That's a IEEE 64-bit type, known in C as a double, which is more than enough to implement this type of filter. Now let's try some quantization effects on it. So I'm going to set up the quantization options here for 16 bits and round a multiple, which is kind of a simple rounding method. You can see there's all kinds of jagged things going on here in the stop band. The pass band is relatively unaffected, visually speaking. So really our concern in coefficient quantization is focused on the stop band of FIR filters. That's kind of a practical observation. You can see here that we didn't come out nearly as well on our specification of 80 dB that we started with. So the method here is to design a filter using ideal, so to speak, 64-bit IEEE floating point numbers, and then to quantize those coefficients and look at the resulting frequency response. Now let's say we over-design this filter. We're going to design it for 90 dB of stop band. But we still only want 80 in real life after quantization. So here you can see that we did better than the 90 dB when we're working with the ideal design system. Let's quantize it again using 16 bits in the rounding method. You can see it didn't do much better there. I'm going to go back to the ideal system. ScopeFIR has a variety of these 4 different methods. Round and round multiple are fairly straightforward. These other 2 methods are search methods. Asymmetric search is the slowest one, but also provides the best results. So that takes a second or 2 to churn, and we get results here that are, let's say, visually speaking, in about the 70 and below range. So we're still not hitting our intended goal at this point, and there's a reason to believe that this is not going to work out for us as it stands. There are some things you can do about this. For example, you might be able to design this as a series of cascaded filters of smaller order. We won't really cover that here in detail, just kind of to touch on it as a possibility. A filter with 300 taps is rather a large filter. Let's try something different, which is going to be a broader transition band. That works in an ideal sense with much fewer taps. I'm going to quantize that again to 16 bits. And you can see that we had a few peaks above this design goal of -80, but we're getting closer. We go back to our ideal design. Now you can see that we're doing better than 80 in every case. We've got some that get fairly close to 80 but don't quite get there. So you could say this was a successful design. We gave up on a few things. We started with 16 bits and we had to give in 2 more bits to 18 bits. We had to over-design the filter a little bit by asking for 90 when we really only wanted 80 in the ideal filter. And we also had to broaden the transition band, meaning this filter is just a little bit wider than it was before that value of -80 begins to happen. Let's look at another example. This is related to what we did before, but with some looser design parameters. Again, the sampling rate is 100 kilohertz. We've got a passband of 10 kilohertz. We've loosened the stop band quite a bit to 20 kilohertz. 1 dB of ripple again. And I'm starting with 90 dB as an over-design point to try to achieve an 80 dB overall quantized design. So I've already got this optimized. We're showing 33 taps for that. We'll quantize it using 16 bits. We get to 80 with no problem. But what about if we want to use fewer, let's say 12 bits? This message occurred because we had one coefficient on each end that was quantized to 0, so 0 coefficients on the ends can just be purely discarded. That makes it a 31 tap filter instead of a 33 tap filter. You can see that we're in the range of about, we can click on this and check, -56. So we put in a design specification of 90. We got out -56. That was because we put in the additional requirement of 12-bit coefficients. So what I've kind of observed as a rule of thumb on FIR filter design is the formula from signal to noise ratio of 6 times the number of bits has been applicable more or less in terms of how deep a stop band can go in a FIR filter design. So let's put that into perspective here. 12 times 6 is 72. You know, very roughly speaking, we're getting in approximately the range of 72. It's always a smaller attenuation than the number you would calculate using that rule of thumb. You could adjust it maybe by knocking off 1 or 2 bits. So let's say this is 10 bits equivalent times 6 gets us to about -60. So these things are rules of thumb, approximation. You really have to try it with your particular design. There's too many parameters to characterize in any simple way. But this gives you some idea that, you know, carry this to extreme. Suppose you want to try to use 8-bit coefficients. Well, there just really isn't any hope of getting to 80 dB attenuation with 8-bit coefficients with this type of filter design as a flat stop band. you notice that we can get to certain points that are deeper than that in the frequency response. But from a Parkes-McClellan design perspective, where the goal is essentially a flat frequency response in the stop band, you know, this may not be what you wanted. Let's say you had decided, okay, I'm going to take 12-bit coefficients, I'm going to take my other parameters, and I'm going to live with the fact that I really want 60. I more or less get that except in a few points, and depending on your application, that may be fine. There's no real reason in a lot of applications that the stop band has to be flat. That's just a kind of a optimization feature of the Parkes-McClellan algorithm. So next, let's talk about the signal-noise ratio formula that comes into this. The textbook formula is 6.02 times the number of bits plus 1.96 dB for quantization noise. And just to make that simple to think about, let's call that 6 times n plus 2. So I recommend you commit either the exact form or this approximate form, 6 times n plus 2, to memory. And in particular, if you want to make it really simple, you can just think 6 times the number of bits. Let's look at compact discs as an example. They have 16 bits per channel. Using our approximate signal-noise ratio formula of 6 times n plus 2, that works out to 98 dB, assuming a full-scale sine wave on the compact disc. Now back on FIR filter design, we can use that same factor of 6 times n. So here we got 6 times 12 bits, giving us 72. And as I said, we knew we'd have to scale that down a little bit. One of the things about quantization of coefficients, it's an inherently nonlinear process. And DSP textbooks often have a chapter about quantization effects. They go into a lot of mathematical analysis about it. In all honesty, I've never approached it that way. I've never used it that way because the math really doesn't fit a nonlinear problem like this. You're ultimately going to have to use some sort of iterative design method, whether it's ScopeFIR or MATLAB or whatever your favorite tool is, to try different things and see what works. So if next time you run upon one of those chapters about quantization of coefficients and filters, you can read it if you want to kind of gain some insight, but in all honesty, you can just skip that and stick with the rules of thumb that I'm giving you right here. So here's a rule of thumb for FIR filter coefficient size that I've developed for the Parkes-McClellan type designs. Again, the emphasis is on the stop band because the other things tend to take care of themselves. It's related to the signal-noise ratio formula we covered earlier. We're expecting the stop band attenuation to be less than 6 times the number of bits minus 2. So in these examples, you could take 16 bits, subtract 2, that gets us to 14 bits, multiply by 6, and we expect less than 84 dB of stop band attenuation. And likewise for 12 bits, that works out to less than 60 dB of stop band attenuation. So remember, this is very much a rule of thumb. It's not an exact formula. It just gives you some idea of what's realistic to expect as you work with your FIR filter design tool. Now, one thing that we can do here that I haven't really talked about very much is the cascade approach. So for this filter that has 33 taps, imagine that we designed two different filters that had, let's say, 16 taps each. We designed the first one with quantization in mind, and it had this kind of non-ideal response that you're seeing here. And then we designed another one that compensated for the response of the first one to some extent, and then had its own quantization. So let's say you have two FIR filters of 16 taps, each having 12-bit coefficients. Well, with one filter like this, maybe you can't get to this level of -80 that we've been using in our design examples. But what you could do very easily maybe is to have two filters, either identical or else similar, that cascade, and they each give a stop band of about 40 dB, and now you have 80 dB to work with total by two cascaded filters. And that's a perfectly good technique. In hardware implementations such as an FPGA, that may make sense. In software implementations, you have different a set of parameters to work with, and we'll talk about that next. Let's talk about the different sort of practical scenarios you run into with word length. There's sort of three basic categories. One is floating point. You've got a floating point processor of some kind. The other is fixed point. Certain DSP processors, especially in the past, were fixed point only. You can still buy those today, like the Analog Devices Blackfin series, which are sort of DSP microcontrollers in effect with a lot of microcontroller capability. And they operate well. They operate with a native design that's based around 16-bit fractional values for coefficients and data. They're amenable to doubling that up to 32 bits, but you do pay a performance hit for essentially two operations every time you're trying to do something or more. Then there are the floating point processors. If you're working with single precision, that is the IEEE 4-byte, that's 32 bits total with some number of bits devoted to the mantissa and some to the exponent. I forget the combination. But anyway, for practical purposes, the float type, as they're called in C. So single precision floating point is fine for any FIR filter application. You're going to be able to get into these ranges of 80 or 100 dB with no trouble at all. So the double precision type, the 64-bit IEEE, is overkill for FIR filters. Honestly, there's no reason to use that unless that's kind of a native format of your processor. It could be that a processor that's designed around double precision is actually less efficient in single precision. I don't really know, but that's possible. And when we're in the fixed point area, the processors have all centered around 16 bits as kind of their basic word type. Let's say we've decided that from our previous story that 16 bits is not enough for this, but we've got a 16-bit processor, so what do? Well, we could break this up into cascaded filters like I talked about a minute ago, or we could use 32 bits. What happens when we quantize this thing to 32 bits instead of 16? As you can see by this frequency graph, the stop band remains essentially flat. No problem. So let's take 32 bits. We'll derate by a couple of bits, make that 30 bits, makes the math easy. Multiply by 6, we get 180 dB. Now what happens if I try to do this filter with 180 dB stop band, which is more than you would ever need for any application I have ever run into. But just to illustrate the point, we'll do that. Takes it a minute to cook through all the optimization process. We doubled our number of taps there. The plot is set so it never shows anything below minus 130 dB. Now we're going to quantize that using our 32-bit search method. This one takes a little bit to complete. So I've adjusted the minimum dB setting of the graph feature here to show down to minus 190 dB. And you can see, looking at this graph, that after quantization with 32 bits, we didn't get to our design goal of 180 dB anymore. We'll check one of these peaks to see what it really is. So that is minus 163. So we lost about 15 dB at this level. And that ties in with our rule of thumb again, that something like 6 times the number of bits minus maybe a couple of bits is what's achievable with FIR filter coefficients. Again, this is very much a rule of thumb. It's different in each case because it's a nonlinear problem. And really you have to experiment with interactively with some sort of FIR filter design tool in order to make these trade-offs among what parameters will result in a filter response that meets the need. But in our Blackfin case, where we've decided to give up on 16 bits and use 2 times that, meaning 32 bits, we can see that this would meet every possible need that you could ever imagine. I don't think I've run into much of anything in my career that had a dynamic range of more than 100 dB. So 32 bits in a fixed point FIR filter is going to be plenty for every application. And likewise, the float 32 bits, it's just 32 bits divided up in a different way with a mantissa and exponent as opposed to representing a fractional value. And in the double, you've got 64 bits to work with, so that's going to be, really far in the extremes here. So when using some sort of microprocessor software implementation, the advice is basically use floating point if that's native to the processor. Use fixed point if that's native to the processor. Double up on the word size if you have to. In a hardware implementation, the common thing nowadays is to use an FPGA. And within that, you often have a free choice of how many bits to use at each stage. It could even vary by stage. And you typically want to minimize the number of bits at each point because the resources used in the FPGA is related to the number of bits. So you may make different choices at each stage in order to minimize the amount of FPGA resources used, but still meet the overall FIR filter design requirement. So to wrap up what we've covered here, use the rule of thumb to get an idea of what's realistic for the FIR filter design specifications that you're working with. Determine what possible values of n bits fits the application needs in terms of implementation, with those 3 basic categories of floating point, fixed point, or FPGA. As the last step, when you have an idea of what the range of n is that's feasible for your application, iterate with your FIR filter design tool to find the specifications and the number of bits that meets the overall filter design need. That's all for this video. Thanks for watching, and be sure and hit like and subscribe to support our channel. Thanks, and bye-bye.